So in this video, we're going to look at three seemingly related functions that have very different behavior at the origin. So let's get to it. The first function we're going to look at is this piecewise function f of x. It's sine of 1 over x if x is non-zero, and it's 0 if x is actually equal to 0. And here's this picture over here, and you see that some crazy or goofy stuff starts to happen as you get close to the input x equals 0, as you get close to the origin in that picture. Now the thing that we're going to focus on with this function is, where is it continuous? And we need to make sure we're all on the same page about what's it mean to be continuous again. What's that definition? So recall that a function f is continuous at a real number a if the limit as x approaches a of f of x is just equal to f of a. So the limit as x gets close to a of your function ought to just be the output at a. And here's a fact about continuous functions. If g is continuous at a, and if f is continuous at the number g of a, then when you compose these, f composed with g, that should be continuous at a as well. And I'm going to try to leverage that fact here, because if I look at the top formula in my piecewise function f here, it looks like I just plugged in 1 over x into sine. And I know that 1 over x is continuous as long as x is non-zero, and I know that sine is continuous for all real numbers. So what we can say based on our fact is that the composition ought to be continuous as long as x is non-zero. So what remains to show, or to explore rather, is what can I say about this function as far as continuity goes at the origin. So it's continuous everywhere else, but I don't know what happens at the origin. We can see that our point moves pretty steadily, but as the x value approaches the origin, we see that the point starts to oscillate more and more wildly. So it's suggesting to us that perhaps this function makes a big jump at the origin. So I'm suspecting that it's not going to be continuous there. So let's take a look and think about if a is equal to 0, then this limit should be the limit as x approaches 0 of my function, but I claim that that does not exist. So how you might see that a little bit more rigorously is, I need to identify maybe two sequences of inputs that get close to 0, right? And that's the x value I care about getting close to, but such that the outputs are, say, never within 1/2 of each other, right? So for example, sine of 1 over x, it's 1 infinitely often in any interval containing x equals 0. And to demonstrate that, right, I can take the sequence of inputs 2 divided by 4n plus 1 over pi. Because when you think about taking the reciprocal of that right there, what are we going to get? We're going to get, an odd multiple of pi over 2 when I take the reciprocal, and I know that sine is going to be 1 there. I should be more explicit. We're going to get an odd number that's congruent to 1 mod 4. So that's how I know the output's always going to be 1. Similarly, though, if I look at the other types of odd numbers, which, are congruent to 3 mod 4, when I plug that into sine, right, when I plug a number like, 3 pi over 2 into sine, or 7 pi over 2 into sine, you get -1 when you do that, right? So the pattern for those is all 4n plus 3 over 2 times pi. So what I'm going to do is I'm going to take the reciprocal of that, and I'm going to make that sequence yn. And just what I want to notice, right, for these sequences xn and yn, as n gets large, as you go further out in your sequence, these things get close to 0. So these are two sequences of inputs that get close to the number that I care about, the input 0 that I care about, such that, though, they are 1 and -1 infinitely often. The points on the top have x values xn, and the points on the bottom have x values yn. And what I'm trying to demonstrate here is that as n goes to infinity, you see that the x values tend to 0. However, the y values that correspond to the points on the top are always 1, and the y values that correspond to the points on the bottom are always -1. So my point is that there cannot be a limit at 0. There's infinitely many peaks and infinitely many valleys, right, no matter how close to 0 that you get. So here's our recap. My piecewise function f of x is sine of 1 over x. When it's not 0 and it's 0 elsewhere, it's sort of badly behaved. It's 0. And so it's continuous when x is not 0, so it's discontinuous when x is 0. So that's what we've shown thus far. And in fact, what I can also say now is f is not differentiable at x equals 0 either. And so recall a little fact here that being differentiable implies that the function is continuous. And equivalently, not being continuous implies that the function is not differentiable. And that's the direction that I use. And that's equivalent because it's the contrapositive. So if you've taken like an intro to proofs class, that should sound familiar to you. The next function that we want to explore is g of x, which is defined as x times sine of 1 over x when x is not 0, and 0 when x is 0. So I've just kind of snuck an x in front of sine of 1 over x. And to kind of see what that does, here's the picture of g, and you see that that x in front, it looks like it wants to shrink the graph a little bit as the inputs get close to 0. And we just want to explore a little bit more rigorously, what does that do? Looks like the point now is moving pretty steadily the whole time. In particular, it doesn't look like there's a jump there anymore at the origin. In other words, I don't have to pick up my pencil when I move across the origin. So I suspect we're going to be continuous at the origin for this function. Now let's explore that idea a little bit more formally. And my first question, well, is this function continuous at x equals 0? So I'm going to argue the same kind of way that g in this case is now the product of two functions that are continuous as long as x is not 0. So it really remains to show just what's going on when what's going on with the continuity of g when x equals 0. So let's think about it. If x is not 0 though, then I know that sine of whatever is always, at most 1 and at least negative 1. And so to say that more compactly, the absolute value of sine of 1 over x is less than or equal to 1. And what that also says is, well, I can multiply both sides by the absolute value of x. So that tells me that the absolute value of x sine 1 over x is definitely less than or equal to the absolute value of x. And what I'm going to do is do a little college algebra. I'm going to unpack that absolute value inequality. That tells me that negative absolute value of x is less than or equal to x sine 1 over x, which is less than or equal to the absolute value of x. And now what I'm going to do is I'm going to take the limit of everything as x goes to 0. And so remember from calculus, limits should respect inequalities. As long as the inequality is true for all your inputs, then the limit will respect that inequality as well. At least as long as it's like a less than or equal to. So when I take the limit as x goes to 0 of everything that I see above, I really just care about what's going on the outsides. And I see on the outsides, they're both 0. So my function, when I take the limit should be between 0 and 0. And this is everybody's favorite theorem about limits. It's the Squeeze Theorem or maybe the Sandwich Theorem, depending on what you're brought up on. So my point is, that allows us to conclude that the limit as x goes to 0 of this function, x sine of 1 over x, is going to be 0. So we've shown, in fact here, that the limit as x goes to 0 of g of x is just g of 0, right? Remember in the definition, g of 0 is 0. So we've shown that the definition of continuity holds at x equals 0, and remember we kind of used some theorems about algebra of continuous functions to justify why g is continuous elsewhere. So in all, g is continuous for all real numbers. Pretty cool. Now we want to move on to another concept. So remember, that's not necessarily enough to say that g is differentiable. So that's the next thing I want to explore about g. So is g differentiable at x equals 0? And before maybe I jump into that, there are also theorems about differentiability, and you know this because you've seen rules like the sum rule, product rule, etc., where it tells me that, hey, here's a formula for the derivative of this algebra of two functions. And what I'm going to utilize here is, well, if x is not 0, you can plug in whatever x you want there, and x is going to be differentiable. Sine of 1 over x will be differentiable also, again, as long as x is not 0. So that top formula, right, you could take its derivative just using the product rule. But I can't necessarily take the derivative of g at 0, right? Where this piecewise function makes that jump in the formula, that's where I've got to justify why should the derivative even exist there if it does. So that's why we're just going to focus on, is this function g differentiable at 0? Just so we're all on the same page about what's it mean to be differentiable, so the definition that I'm taking here is g is differentiable at x equals a, so it's some real number a, if the following limit exists. And if you study that limit closely, that is just, you're trying to define, you're taking the limit as h goes to 0 of the slope of the secant line to g through the points a plus h and a. So that's really just a slope there that we're taking the limit of. So as long as that is a real number, so I'm implying that it should exist, so I'm not going to let that be infinity or negative infinity. Now if that's a real number, then what we'll do is we'll call that the derivative of g at a, and then we'll all denote that by g prime of a. So I've got the secant line here from 0 plus h to 0, and as h goes to 0, that purple point gets close to the red point. What I want to notice is when it passes over the origin, the slope of the secant line goes nuts, and it never settles down on an actual number. So I'm pretty sure the slope of the tangent line probably doesn't exist at 0. Now let's show that a little bit more formally. So that's our definition we're going to work with. Now what's going on at a equals 0? Then let's compute this limit. So the limit as h goes to 0 of g of 0 plus h minus g of 0 over h. That should be, well, the limit as h goes to 0 of h times sine of 1 over h. That's the first part, which is really g of h, right? Minus g of 0, so that's that 0 over there on the right, all divided by h. And what I hope you notice is that the h's cancel. So I'm just left with the limit as h goes to 0 of sine of 1 over h. But what we talked about in the previous problem is that that limit doesn't exist. So this limit doesn't exist. So that justifies that crazy wiggling that the graph was doing in the little video, in the Desmos demonstration. So that justifies that the tangent line does not have like a well-defined slope, right? So this g is not differentiable at x equals 0. And so note that g is differentiable for all x not equal to 0, and that's what we talked about earlier, where, otherwise it's a product of two differentiable functions, right? There's nothing wrong with x, and there's nothing wrong with sine of 1 over x, as long as x isn't 0. So let's go on a little tangent here. So as a tangent, it was believed until the 19th century that continuous functions could only fail to be differentiable at isolated points. And that's this situation, where I've got a function that's continuous, x times sine of 1 over x. It's continuous everywhere, right? But x equals 0 is sort of this weird point that hangs out on its own where it's not differentiable. So some mathematicians thought that this was kind of the only behavior that continuous functions could have. So most of the time, continuous functions are pretty nice and differentiable, right? They're not too jagged. But in fact, in the 19th century, Carl Weierstrass, who actually came up with the modern definition of a limit that we use, so if you've seen some epsilons and deltas and whatnot, you can thank Weierstrass for that. Weierstrass proved that this intuition was wrong. And what he did was he exhibited a function that is continuous for all real numbers, but is not differentiable at any real number, which is pretty crazy. And then a little bit later, this idea of like trying to find these sort of pathological functions like Weierstrass did, it's actually sort of a method to do it. And so the existence of such a function was a little bit more easily obtained later in the 20th century via what's called the Baire category theory from topology. So if you find any of that stuff interesting, I encourage you to go look that stuff up and read about it a little bit more. And the last function that I want to consider is, what if I throw an x squared in front of sine of 1 over x if x is not 0, and still continue to let the function k be 0 now if x is 0. So here's a picture of that one. And what do I see? I see that x squared, it shrinks the waves even more than the regular old x did as you get close to 0. And just like above, I'm not going to write down a justification for why this function k is continuous at all real numbers. It's going to be similar Squeeze Theorem type of argument you could use. And I'm also going to leverage the fact that x squared is differentiable as long as x isn't 0, and sine of 1 over x is differentiable as long as x is non-zero. So like their product will also be differentiable as long as x is non-zero. So again, it remains to show, is this function differentiable at x equals 0? So I've got the secant line from 0 plus h to 0 again, and now what I notice is that as h goes to 0 and that red point wants to get close to the blue point, the secant line's slope looks like it settles down quite a bit. It looks like it settles down to a horizontal line. So that tells me that the derivative ought to exist here. Now let's look at that a little bit more formally. What we'll do is we'll just compute what is this difference quotient whenever I plug in 0 for a. So the limit as h goes to 0 of k of 0 plus h minus k of 0 divided by h. When I plug that stuff in, the first part's just k of h, so that should be h squared sine of 1 over h. K of 0, if you look at the piecewise function, when you plug in 0, you get 0, so that's why that minus 0 is over there, then all divided by h. And you see kind of the key thing here, the h squared over h, just an h is going to cancel, but you're still left with an h out front. And what we justified earlier is that when you take this limit, you use the squeeze theorem here to say that this limit is in fact equal to 0. So here we proved that the tangent line has slope 0. And remember, the way that we'd say that in symbols is say k prime of 0 equals 0. So the derivative exists at 0. So in fact, k is differentiable for all non-zero x as well, and that was my spiel about how it's the product of two good differentiable functions as long as x isn't 0. And so thus, altogether, we could say that k is a differentiable function for all real numbers. And remember what that implies, right? Remember, being differentiable implies that the function is continuous there too. So because k is differentiable for all real numbers, we can say that k is continuous for all real numbers as well.